Hello, good afternoon. Today we are going to look at mutual recursion or recursions which involve multiple functions. The idea is that one function calls another function and that function calls the first function recursively. So they both together are recursing with each other. For example, it can be that you have a function int func1 and inside that function you might call func2, okay, and func2 might be different function, and inside func2 you will have func1. You have a call to func1. So you can see func1 calls function 2 and func2 calls func1, and so they mutually are recursing with each other. You should realize the same principles we used in recursion should apply here. What are those principles? The principle that the parameter value should decrease every time as the second func1 call gets called, the second recursive call of the same function gets called, the parameter value has to decrease, right? If you can show that it decreases, it means that good, there is our recursive function is going to stop. If it's not decreasing, we're going to go into an infinite loop. It never stops. So this is the main idea on mutual recursion. Now, to understand this mutual recursion, we will try to write a program which solves the Tic Tac Toe game. I hope you know the Tic Tac Toe game. Basically, there's a board of 369 cells and you are supposed to put X or O in each of these locations. If there is a line of X's, either a horizontal or a vertical or a diagonal line of X, then the X wins. On the other hand, if it's a line of O's, then the person O wins. That's tic-tac-toe game, and like people alternate, the player alternate. After X player plays, the O player plays X, right? They keep on alternating. Now, so that's tic-tac-toe game. What are the two functions which are going to mutually recur? The two functions are going to be what is the play for the X player. The X player's decision is bound on the decision of the O player, right? What the X player decides to play is dependent on what the O player is going to play once the X player plays this, right? So that's going to be the mutual recursion. So X player is going to call the O player and see what the O player will play. In turn, the O player will call the X player's function, right? And then that's going to mutually recur. So that's the main idea. And to start the process, I already created a board here, board position of X and O's here. I have marked two positions X and O, and I already written the print function to print the board. This is something we already saw in the previous lecture on how to print a board for the Sudoku game. It's the same it's basically the same function has been copied, right? So that's it. So I can print the board here and see how it's going to get printed. Right, so it's printed like as we wanted. X and O's are printed. What should the X player play now? So let's assume that it's the X player's turn. What should that player play now? Okay, that's what we want to. So I'm going to have a function which basically returns int X play or X move. Okay, what should the X player move now? And what does it take? It's going to take the board first of all. What will the X player do? X player is going to go through all the cells in the board. So that's I'm going to write that now. It's going through all the cells in the board. Right, and it's going to put, first of all, that board position should have the blank symbol. Okay, it's not already marked. So that's first check. So if it's already marked, so if it's not equal to blank, that means it's already marked. In that case, what do? I continue. I go back to the for loop again. Now I reach here. Here only if the board ij position is blank. Is that clear? Yeah. Now what do? I'm going to assign ij position to, I'm going to put that mark the ij position with x, and then I'm going to call the players move. Okay, I'm going to call the players move, and now the player can return. The return is going to be one of the few things. The player can say, right, I'm going to win from here, and if I'm going to win, the player is going to give me the cell position where the player is going to mark that. Okay, so how is the cell going to be? The cell is going to be marked like this. This is going to be, so because I can only return an integer, I'm going to assume the following. The first position is 1, second 2, 3, 4, 5, 6, 7, 8, 9. These are the cell positions. Okay, so if the O player returns a number between 1 to 9, it means he is going to play O in that position. If O player plays at this 8th position, he can win. That's the idea. Okay. On the other hand, if he returns 0, he is going to lose, and if he returns -1, it's a draw from that. So I'm going to make two more constants. Let's make constants for draw. What did we say? 0 or -1? I just forgot. So let's put draw it to be -1, and hash define used to be 0. So this is how it's going to be, and if it's a number from 1 to 9, it's going to be one of the positions, which means it's a win for the player if the player plays the game at that point. So that's how it's going to be. So I'm going to return, this is how I see it. So success equal. So I can write that the function returns a position in the board numbered from 1 to 9 if the player can win will surely win from there, right? If the X player is going to surely win from there, it's going to return that point. It returns draw or -1 if it's draw from that position, and it returns this if it is a so it returns a lose 0 if it's a lose from that position, no matter what. Is that clear? Okay. So if it's success, let's take. So now the O move has returned success. Now what is if the success return is turned as a loss? It means that the O player is going to lose from that position no matter what. What does it mean? It means that now I can this board position which we have played, right? IJ position which we have played, that's a good move, right? That's a position from where we are going to win for sure. So I am going to just return that value. How do I get that value? I have to return a number from 1 to 9, right? So on the other hand, this IJ values are going to be numbered from 0 to 2, 0, 1, 2. And I want to convert that pair 0 and 2 into numbers from 1 to 9. What I do is that I'm going to multiply I into 3 plus j plus 1. As you could see, if I substitute I and j to be 0, what is the value you get? 1. So that is 0, 0 is basically this 1 point. And what about 2, 2? 2, 2 is 6 plus 2, 8 plus 2, 1, 9. So that's the last point. Next thing is we need to check if What should we do if it's a draw? If it's a draw, I need to store that information because this move made into a draw, maybe a different move by X would have meant a win, right? So I can't return right now because a win, if I know for sure a move is a win, I can return saying that okay, you just play along that line and you're going to win. But if it's a draw, I'm not going to play that because there might be another move which can lead to a win. So I'm going to store that information that is a draw, and so I'll note down this information outcome. So let me call it variable out, which is now going to be draw, right? Now, on the other hand, if success had returned a big number, that is a value which says that number greater than 0, which says that a number from 1 to 9, then it says that the O player has a win using that move, right? In that case, what should I do? In this case, then I am supposed to move it back to blank, right? So one more thing, I have to change that the board back to blank here also because we had returned, I should return the board exactly like it was when it came here, right? Because maybe in the recursive code above it's going to take a different path, but already marked it with an X and things and going to create havoc. So I'm going to return it with the board exactly like it was, and the board it came at blank at the ijth position. That's why I did that. Now I check whether board ij is I set board ij to be blank. If it's going to win for the O player, I set the ij position to be blank, and then I continue doing this for loop. That's all. This is good, and I'm going to declare the variables. First, outcome is I'm going to set outcome to be default to be lost, because if the outcome never got changed and it never returned, it means that it's a loss. So I can basically do it here. If outcome is a loss, then I'm going to return loss. So this is basically the base case. What is the base case here? The base case is basically there is no more board position to play. No more position to play, and I have that now. So it's basically like full. It's default set to 1, and it's 0. This is exactly same like we saw in the Sudoku. And so if it's full, if the position is, if the board, there's nothing more to put in the board, if it's full, then what I'm going to do is the following. If it's full, I can basically return I'm going to return draw. I'm going to return draw. Okay, so this much is good, but I missed one crucial thing. I never checked whether when I put X here, right? So that's the one base case I missed. So this is okay. Like the base case. Right? If the board position is full, it's a base case. I return one more base case. The base case is that if I put this position X to a point and I win from that position, I can return that position. So I'm going to write a function check whether a board position is a win for X. So int is win, right? Board so pass pair type, whether it's X or O. I'm going to see what is it I need to check. I need to check whether there is some row, there is some column which contains all X, then the win for player X. Similarly, if there is a row which contains X, it's win. How many times the player is that particular turn. Yeah, it's a win. Because the player there is wins where the player wins. For the row, anything for finally for the two diagonals. So let's write it for the diagonal. For this first diagonal, it's all if board 0 0 board. I'm going to say it as board 0 0 is equal to player. Then I'm going to say 1 1 equal to board also equal to player. All three are players, then it's a win. So that's one diagonal, and the other, right, the next diagonal here is 2 2 1 1, not 2 0 2, right. And if any other case, I'm going to return function returns 1 if it, right. That's what this function. So if this is the case, what I'm going to just check is if board is win board for player X, right? The win for the player, then what do I do? Make it to blank, I set it back to blank, just like we came into this function. I'm going to return. Yeah, so if it's a win, again I return. So I check the board position and then return. I put a basically I put an X mark in one of the board position and check whether it's a win. If it's a win, I return. That's basically the base case. And another base case is always when it's full, the board is full and there's nothing more to put, I return it as a draw. Okay, so these are the two base cases we have seen. So you can see that the base case is very subtle, it's not clear, right? And another thing, so now so this is I have written for the X player, right? But this X player is going to call the O player's move, and basically we are like turning. If the O player is successful, then I don't want to play that game, so I keep on. But if the O player is going to lose for sure in a particular move, the move player is going to play. So that's the turn we do, and this is exactly what we are going to do. So now we are going to write the function for O player, and it's going to look almost similar. I'm going to replace X by O, and right. exactly what we would. And so basically this is now turned because they are symmetric in each other. The X player and the X player's move and the O player's move are symmetric. Okay, I think this should work, and let's just see what happens. So in this position, I want to know what is the best move for X. Okay, what is the best move for X? Best move for X. So, GCC factor. Yeah, that's wrong. Do you know what is the mistake? So this is one reason why looked into this mutual recursion, because okay, again, think what is happening. The compiler is coming from top. It's coming here and it sees OMU. It comes here and it sees the function xmove. But this function xmove, it does not know what the function x, right? Because it's defined later. This is something we said compiler is not going to accept if things are defined later. The compiler should know that it's I mean it should see before a function is called, it should know what that function, right? But now, can I put this function on top? Is it enough if I put this xmove function on top of omove? Then this won't create a problem. Again, that's going to create another issue, because xmove calls omove, and the compiler would want to know what is omove before it's used, right? So that's why. So it's because of mutual recursion. The compiler want to see, to know what xmove is, it needs to know what omove is. To know what omove is, it needs to know what xmove is. So it's now tricky. So that's what we had seen this thing earlier. Two methods to resolve this thing. One method was to basically put the block of the function defined on top and expect it to get resolved, but that cannot be done here because of mutual recursion. And therefore the next method to do the resolve this thing is to define xmove here. That is, we are only going to tell the compiler what xmove is going to look like. So I'm going to just tell that xmove is going to just look like this, and you are going to see this thing later. Okay, just told the compiler that xmove is a function which you are going to see later. I don't know, right now I'm not going to tell you what its contents are. I'm going to just right now I'll just tell you what its type is. The type is this. It takes as a character the board dimensional array as an input, and it returns an integer as output. So that's the type you're going to see. Okay, I told the compiler that, and now compiler is saying there's some warning here. What is the warning? Some function has been returned without the 70. Yeah, supposed to return something. Function is supposed to return something. I mean, how will it come even reach here? Sorry, the outcome was a draw. It's going to reach here. Then I should have returned it's a draw. So I'm going to return out. Yeah, so no matter what, I'm going to return outcome. So outcome is equal to loss. Is not something we need to have. So just remove that and same here, and remove that, and do. So it's saying move for x player is equal to 1. Now thing asking us to play here. So let's try to play there, and I'm going to, so the computer is basically the player X, and I'm the player O. So computer says, okay, just go and play there. Let me say I just played there for X. Then what should be the, so X is played here, right? So what is the best, where should I play? I should play in here, because it's going to be an immediate win for the computer. So I just played O here. Now I'm going to ask the computer again, what is the best place to. Computer is saying play at 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Asking me to play here. Brilliant. Play there. You can see. So the computer has basically played here X. Right? Now I am trapped. I can either go and prevent this thing by playing here, or I can play here. Where do you want me to play? Okay. Try here. Oh. I'm going to ask the computer again. Where should. Computer says play at 6. Right? Asking me to play here. That's it. The win. That's win for the machine, and that's good to see that we have basically made a game, AI game, right? Computer easily beats me in Tic Tac Toe now. So, right. So that's it. So to conclude, what are the few things we saw? We need to notice few things before we conclude. One, the base case returned correctly. So the two base cases are basically here, and we need to check whether that's returned correctly. That's one thing we need to notice. And second thing to notice is that is the recursive step, there is a decrease in value in the recursive step. What is the decrease in value in the recursive step? As you could see, the recursion is now a little tricky because xmove is now going to be called here, right? Once the omove is called, then that omove calls xmove, and then there the recursive step is. So it's a little tricky. How do we now notice that there is a what is the value which is now reduced? What we can see is that what has basically reduced is that the number of blanks in the board, in the tic-tac-toe board, has reduced. That's what you need to see here. The number of blanks has reduced, and that's why this the recursive step stops after some time. So the blanks are reducing at every point, and there are only like 9 blanks at most, and then it has to stop after at least 9 rounds. So this is mutual recursion. Thank you.